going to continue our discussion of ionic compounds and ionic bonding to take a look at how we can predict the formulas of ionic compounds and also understand some of the properties of ionic compounds that result from the ionic bonding that's present holding them together. So first of all, it's important that you be able to predict the formula, the chemical formula of an ionic compound. And here is the key principle that you're going to use in order to make that prediction. In order for a substance to be stable, it has to be neutral, no charge. So all atoms, in order to exist stably as atoms, have to be neutral. If they react to form cations and anions, and we make a compound from those, then the total of the positive charge from the cation and the negative charge of the anion, that total has to add up to 0, or in other words, neutral. So we can use the periodic table and the octet rule to help us predict charges that atoms would form when they become ions. So family 1A, the alkali metal family, we know that they have one valence electron, and just as we saw in the formation of sodium chloride, all of the alkali metal elements will lose one electron and form +1 cations. Family 2A, the alkaline earth metals, they have two valence electrons. In order to achieve that octet in their energy level directly below, they're going to lose those two electrons to have an octet directly underneath. And so we see the alkaline earth metals forming +2 cations. This is always the case when we find them in ionic compounds. Transition metals, it's a little more complicated. They can usually form more than one kind of cation, and that's the result of the influence of the d electrons. Remember, transition metals, their last electrons are heading into d orbitals, and although these are not technically valence electrons, they do influence their chemical reactivity. So transition metals usually form more than one kind of cation. And this is an excellent time to remind you that I pointed out the table of ions that you're responsible for memorizing, found in the back end of your lab manual. So you should have that table of ions somewhere where you're looking at it regularly. You're going to have that information memorized in a fairly short amount of time, and it's good to get a head start on it and start the memorizing now. If we go to the nonmetal side, we see the halogens, family 7A, with those 7 valence electrons, just like we saw with chlorine's reactivity in forming sodium chloride. The halogen family with those 7 valence electrons want to gain 1 electron in order to achieve an octet in their valence shell. And so the halogens will form -1 anions when they are in ionic compounds. So we're talking here about this particular type of compound. It turns out that the halogens, as well as most all nonmetals, can also do a different type of bonding, covalent bonding, that we'll get to in the next topic. But if we're looking at a halogen in an ionic compound, we would predict its charge to be -1, gaining 1 electron to form an octet. Now oxygen and sulfur, they're in family 6A. They are the most reactive of their elements, of the elements that are found in that family. They have 6 valence electrons. They would react to try to gain 2 electrons and become -2 anions if they're going to form an ionic compound, if they're reacting, in other words, with a metal. But again, they have some other options that are available to them with covalent bonding that we'll talk about later. So we're typically seeing just oxygen and sulfur in family 6A forming anions with -2 charge. Nitrogen, family 5A, 5 valence electrons. So how many extra electrons would it need to gain in order to have an octet, to have 8? It would need to gain 3 electrons, and therefore if we find nitrogen in an ionic compound bonded to a metal, then its charge would be -3, gaining those 3 electrons to have an octet in its outermost shell. So here's a question that you could see on a quiz or an exam. Predict the formula of the ionic compound formed from magnesium and fluoride ions. Well, we just talked about those ions. Magnesium, an alkaline earth metal, it would lose 2 electrons to form a +2 cation. Fluorine, a halogen, when it reacts, it gains 1 electron and now is called fluoride and has a -1 charge. But I can see here that if I take the +2 charge on magnesium and add it to the -1 charge on fluoride, those 2 charges are not going to add up to 0. I'm not going to have a neutral compound. So what am I going to do when I write the formula? Knowing that all charges have to add up to 0, I'm going to put a little subscript 2 with the fluoride, indicating that I need, in the huge 3-dimensional array that is formed by these cations, remember, all ionic compounds, when you find them, they're a huge 3-dimensional array, and this formula is the simplest whole number ratio of the ions that are present in that array. If I counted all of the magnesium ions and all the fluoride ions present in the array, I would see that the ratio is 1 magnesium to 2 fluoride. And the math totally checks out. We have the +2 charge on the magnesium. Each fluoride has a -1 charge, and there's 2 of them. So 2 times a -1 is a -2. And the total charge from the positive ion and the negative ions totaled adds up to 0. So again, all positive charge and all negative charge in the formula has to total to 0. So one more time illustrating, as we did with sodium chloride, the formation of magnesium fluoride. So we've predicted that its formula is MgF2, its simplest whole number ratio formula. How can we illustrate the formation of magnesium fluoride from magnesium atoms and fluorine atoms? Well, here's the Lewis dot structure or electron dot structure of magnesium. It has those 2 valence electrons. We see that from its abbreviated noble gas configuration. Here is fluorine, family 7A. So I'm drawing the 2 fluorine atoms with their 7 valence electrons using the noble gas abbreviated configuration below it. And what's going to happen? We're going to see electron transfer taking place. But fluorine does not want to gain 2 electrons. It only wants to gain 1. So each fluorine gains 1 of the electrons that the magnesium is going to lose as it forms a +2 cation. Each fluorine gaining 1. And then we have on our product side our magnesium, now with its +2 charge as a +2 cation, and each of the fluorine now called fluoride because they have gained an electron and are now an anion. So showing the fluoride and making sure that I indicate that it is now a charged particle with that negative charge. Note, I'm not going to put my second fluoride in this position. Why? because I know that negative charge repels negative charge. So just to get a little better idea of what's happening in the three-dimensional array, I'm going to put my second fluoride anion on the other side of the magnesium cation. So I'm illustrating this electrostatic attraction that is the heart of all bonding, both ionic and covalent. So, one common misunderstanding that I encounter when I grade papers is if I ask a student to explain what an ionic bond is, they almost always start out with the words, an ionic bond is a transfer of electrons between a metal atom and a non-metal atom. And although there's aspect of the process that they're on the right track with, that is not what the bond is. The bond is not electron transfer. What is that bond? That bond is the electrostatic attraction between the oppositely charged ions. So yes, you did have to have electron transfer to create the oppositely charged ions, but the bond itself is this electrostatic force of attraction. Positive and negative charge attracts. That's what the ionic bond is. And if I had a model of magnesium fluoride, it would be this large three-dimensional array where magnesium ions are surrounded by fluoride ions on all sides and fluoride by magnesium. Looking at the configurations, we see that magnesium now has an octet in its second energy level directly below what was its valence, and each fluorine now has an octet in their second energy level. In other words, each fluorine now has a configuration like that of neon. So the octet rule is driving what's happening here in the transfer of electrons to form the ions and in the formation of the ionic bond. Now, if we want to take a look at properties of ionic compounds, we can see that the properties directly result, properties of ionic compounds, from the nature of the ionic bond. So what do we observe with ionic compounds? Right, so we observe, making a little room down here, we observe that ionic compound properties, we observe that they are hard, right? That they are crystalline, right? That they are brittle, these are all properties that we observe with ionic compounds. And one last property, they have arrow up, meaning high. They have high MPs. Remember, we talked about that. MP, abbreviation for melting point. And also, they have high boiling points. Right, so ionic compound properties, hard, crystalline, brittle, high melting points, high boiling points. These properties directly result from the nature of the ionic bonding. Right, so going back to the sodium chloride example, the hardness of sodium chloride table salt, right, strong ionic attraction between the oppositely charged ions. The crystalline structure of ionic compounds indicating the very ordered arrangement that happens in the three-dimensional array as the oppositely charged ions arrange to maximize their attraction, right, to their counter ion of opposite charge. The brittleness, the fact that if you hit an ionic compound with a hammer or a hard object, it just crumbles apart. What's happening there? Well, if I hit the ionic compound, in this instance sodium chloride, with a hammer, I can physically displace the array and cause a sodium ion that was in this position to be forced down by a blow downwards, and now it's lined up directly with another sodium ion. Positive charge, repulsion happening there between like charge, and the crystal just cleaves apart because of that repulsive force experienced when you displace the array by putting a force, a blow upon it. The high melting points and boiling points are an indication of the strength of the ionic bonding, the attraction of the oppositely charged ions, and how much energy would be required to either melt them, convert into a liquid, and then even more energy to vaporize, pull the ions totally apart from each other. So it's important to note that all ionic compounds are solids at room temperature. All ionic compounds are solids at room temperature. And that's directly related to their high melting points and their high boiling points.